It's my pleasure to welcome Sebastian Kamann to our seminar. Sebastian obtained his PhD at the Institute for Astrophysics, or AIP, in Potsdam in Germany, working on globular clusters and also developing quite a famous reduction software tool called MUSE for the MUSE instrument. He did his first postdoc at the Georg August University in Göttingen and later moved to the Liverpool John Moores University in the UK. He was recently awarded the Future Leaders Fellowship of the UK Research and Innovation Programme, and he since was awarded permanency at this university. So without further ado, go for it.
Thanks very much, Thomas, for the nice introduction. And yeah, thanks for having me and giving me the opportunity to talk about some recent work that we've been doing on star clusters and in particular the black holes in them. And I think these are quite exciting times to study black holes, because it seems they popped up everywhere over the last years. The most famous discovery was without a doubt the detection of gravitational waves, first detected in September 2015 by the LIGO Observatory, which was then awarded a Nobel Prize only 2 years later. And now LIGO has seen 3 observing runs so far, and this resulted in about 50 detections of gravitational waves, mainly from binary black hole mergers. I'm showing you here on the right the signal that was detected for the very first black hole merger ever observed this way. But also at a very different mass scale, there has been remarkable progress about our understanding of black holes. What you can see here on the left is the first picture of a supermassive black hole. The supermassive black hole in the galaxy Messier 87, the central galaxy of the Virgo cluster. This black hole with a mass of the order of 6 billion solar masses is one of the most massive black holes we know of in the universe. And the picture that you see here, created by the Event Horizon Telescope, was really created by combining radio telescopes essentially all across the globe. More recently, this picture also received an upgrade, and we can now even see the polarization in this ring around the black hole, and can use this to study the magnetic fields around the black hole. And then finally, last year, also the most recent Nobel Prize in Physics has been dedicated to black hole research. And it was shared between a theorist and 2 observers. So Roger Penrose received the Nobel Prize for his prediction that black holes are actually a direct consequence of the general theory of relativity. And here on the left, you see the Penrose diagram for a black hole. And then on the observational side, Andrea Gies and Reinhard Genzel received the Nobel Prize for their groundbreaking research on the supermassive black hole in our own galaxy, the Milky Way, which they discovered by studying the motions of stars over several decades and using the stellar orbits to infer that our galaxy must harbor a supermassive black hole of the order of 4 million solar masses heavy. And all this research led to the following picture that we have now about black holes in our universe. So I'm showing here kind of a toy model or of the black hole mass distribution in the universe, where you see kind of a clear bimodality between the stellar mass black holes at the low mass end. Highlighted here is the mass of the first gravitational wave detection. And then you have a big gap, and then you have the supermassive black holes on the massive end of the mass scale. Just here you have the black hole in our own Milky Way and the black hole in M87 would be located somewhere around here. We know that stellar mass black holes are the remnants of massive stars. And we know that supermassive black holes are usually found in the centers of galaxies. But what's quite striking about this diagram is that there's this distinct gap at intermediate masses. We can explain where this gap comes from the stellar mass side, because it is believed that if you go to higher and higher stellar masses, at some point you come to the regime where stars, when they explode as supernovae, explode as so-called pair instability supernovae. And as opposed to normal supernovae, these supernovae wouldn't leave a black hole as a stellar remnant. So that explains why you have kind of a sharp cutoff at the stellar mass black hole spectrum. But there has been a lot of research about whether there are actually black holes in this mass gap. And these black holes would, if they are discovered, then be termed intermediate mass black holes. Now, if we look at the kind of a family portrait of the stellar mass black holes that we know of so far, then it looks like this. So in this, kind of artist's impression of the black holes we know of, you have all the detections made by LIGO and Virgo so far in blue, and what's always shown is the masses of the two progenitor black holes and then the mass of the newly formed merged black hole. And if you look at the progenitor masses, then you see that the overwhelming majority actually seems to be below a limit of the order of 70 to 80 solar masses, which is exactly this limit which is predicted because of this pair instability supernova gap. However, there's one candidate in here, which is this one, where even one of the progenitor black holes had a mass in excess of 80 solar masses. So it already seems to fall into this pair instability gap. And this event, which was recorded on the 21st of May in 2019, is actually remarkable for two reasons. First, because, as I mentioned before, at least one of the progenitor black holes fell into this pair instability mass gap, which suggests that maybe this black hole was already formed by a merger of two lower mass black holes. The same might actually be true for the second black hole, which with the mass of 66 solar masses is already pretty close to this mass gap that's predicted. But also what's interesting is that the resulting black hole with a mass of 142 solar masses, it's the first black hole that's actually really detected in this intermediate mass black hole range, which is usually postulated to be between, say, 100 solar masses and maybe 10,000 solar masses. But all these mergers between stellar mass black holes, they bring up the question of where do black holes actually find each other? And I don't want to go into too much details about this, but there's actually mainly two scenarios that have been proposed. On the one hand, you can have massive binary stars, so a binary of two stars massive enough to form black holes via supernova explosions at the end of their lifetimes. And then over a Hubble time, the resulting binary black hole could come close enough together to actually merge. An alternative would be star clusters, which like the famous one shown on the right here, which is R136, the central star cluster of the Taranto Nebula in the Large Magellanic Cloud, which is probably very well known to a few people in the audience. This is the most massive star-forming region in the local group. And these star clusters are kind of a natural habitat for massive stars. For example, in this particular star cluster, the most massive stars have been found to have masses in excess of 150 solar masses. Now, if you have a lot of stars on such a small volume, that seems to make hierarchical mergers, like what seems to be required to explain this very massive gravitational event. These hierarchical mergers appear really feasible in these high density environments. However, if you look at this more in more detail, then you find that star clusters are actually very insecure hosts for black holes for two reasons. The first is their shallow gravitational potential. The second is their short relaxation times. If we look at the shallow gravitational potential, this can become an issue in two instances. First, when the black holes are formed by supernova explosions, what can happen is that they receive natal kicks that have a high enough velocity to eject them from the clusters. Now, since clusters don't live in their own dark matter halos, you only need a velocity in excess of, say, a few tens of kilometers per second to remove a newly formed black hole from the star cluster. But also mergers can become an issue. What I'm showing here on the right side is a plot from the paper by the LIGO collaboration on the discovery of this intermediate mass black hole, where they predicted the velocity that the newly formed black hole would receive following the merger. And for this merger, it was found that most likely the spins of the merging black holes were quite misaligned. And this would lead to a very high kick velocity that the resulting black hole would receive. You can see here for two different scenarios that they went through, the probability density for the kick velocity of the newly formed black hole. What's shown in dark green here is all you need to escape from a massive star cluster. So even if this intermediate mass black hole formed in a star cluster, it's highly unlikely that it actually was retained by the cluster. Now, if you have a nuclear star cluster, which would sit in the center of a galaxy and hence in the center of a dark matter potential, well, then things would look a lot different and the probability of retaining such a black hole would be much higher. Depending on how misaligned the spins were, it's actually also feasible that this black hole could be ejected from a galaxy like the Milky Way, or in extreme cases, even from a very massive elliptical galaxy. But these kick velocities aren't the only problem. Another problem is that star clusters are very dynamically active systems. And what can happen in a star cluster is the following, which I tried to illustrate here. If you form a new star cluster, you'll form some massive stars shown here in blue and some low mass stars shown here in red. Now, at some point early in the evolution, the massive stars will explode as supernovae and give rise to the formation of black holes. At some point in the evolution of a cluster, there's the time when the black holes are much more massive than all the remaining luminous stars. And then they will undergo severe mass segregation and will actually all accumulate in the center. And it has been predicted already by Lyman Spitzer that in such a case, the black holes would form a self-gravitating cluster inside the cluster with a very short relaxation time. And then interactions between the black holes would lead to their ejection from the cluster over quite a short amount of time. However, recent N-body simulations suggest that this Spitzer instability is actually not as efficient as it has been previously thought. Now, if we want to look for black holes in massive star clusters, what's the situation that we have in the Milky Way? Now, the massive star clusters in our Milky Way are really, this population is really dominated by the old and massive globular clusters. So star clusters typically more massive than 10 to the 5 solar masses that formed of the order of 10 billion years ago. So if this Spitzer instability would be as efficient as it has been previously suggested, then these star clusters should essentially be completely devoid of black holes. And this had this was kind of the common sense for a lot of decades. But as I mentioned before, with recent dedicated simulations, it has been found that we expect sizable black hole populations, at least in some of those clusters. What I'm showing here is the results from a suite of dedicated Monte Carlo simulations carried out by Ascar et al. 2018, where you see the predicted number of black holes for a range for different star clusters for different globular clusters in the Milky Way as a function of their absolute magnitudes. So if it's true that globular clusters can actually hold to sizable populations of black holes over the lifetimes, then those star clusters would actually be prime candidates for searching for black holes. Incidentally, globular clusters may also help us to uncover this unknown population of intermediate mass black holes that has been suggested to live in between the two extremes. Why is this? Well, we know from the supermassive black holes that the supermassive black holes scale very tightly, their masses scale very tightly with fundamental properties of their host galaxies, such as what's shown here is the relation between the mass of the supermassive black hole and the velocity dispersion of the host galaxy around it. And you can see this nice correlation. Similar correlations exist with stellar mass or luminosity. And now a naive idea would be, well, if we extrapolate this into the stellar cluster regime, then in something like a star cluster of 10 to the 5, 10 to the 6 solar masses with a velocity dispersion of 10 kilometers per second in the center, we would expect to find something like a central black hole of the order of 10 to the 3, 10 to the 4 solar masses. Now, it's usually not a good idea to extrapolate power laws over different orders of magnitudes, but there's also more physically profound ideas why we should search for massive black holes in star clusters. For example, if we look at the Milky Way, then we know that it's surrounded by the Sagittarius stream, which is essentially consisting of debris of the Sagittarius dwarf galaxy, which has been accreted by the Milky Way over the last few giga-years. And in the core of this Sagittarius stream sits M54, one of the most massive globular clusters in the Milky Way. And we have firm evidence that this star cluster is actually the former nuclear star cluster of the Sagittarius dwarf galaxy. Now, if this dwarf galaxy contained a massive black hole before it was accreted, then why shouldn't it still exist in M54? Now, the M54 might be the most obvious case, but since Gaia, we know that our Milky Way actually underwent several accretion events. The most famous is probably the Gaia Enceladus event, which was discovered after the Gaia data release 2. And here I show a plot from a paper by Diederik Cruyssen et al., where they kind of made a nice plot of all the different accretion events that have been predicted or are known as a result of the amazing Gaia data that has become public. So you have Sagittarius here, which was the most recent merger, Gaia Enceladus before that, and then there's a few other events that happened in the very early stages of the Milky Way. A while ago, in a paper led by Joel Pepper, we looked at which of these progenitors had nuclear star clusters that we can probably still observe in the population of globular clusters in the Milky Way. And we came to the conclusion that apart from M54, there might be 3 additional former nuclear star clusters hiding in the Milky Way. The most famous of them is probably Omega Centauri, the most massive globular cluster in the Milky Way. All right, now we know where to search for black holes. Now, how do we catch them? one of, unless you have a binary black hole, probably studying the motion of stars around it is the most secure way of detecting a black hole. And obviously, if you want to find many black holes, the more stars you can study, the merrier. However, radial velocity or velocity studies of black holes, especially, velocity studies of stars, especially if you want to perform them over extended periods of times to resolve binary orbits and the like, are very cumbersome. And only recently, I think we started acquiring the data that you need to study velocities of large enough stellar samples in order to do a census of black holes in and around the Milky Way. On the proper motion sides, you can use Gaia data, especially in the future when they'll publish the binary orbits, and you can also use HST proper motions. And on the and on the radial velocity side, I think integral field spectroscopy is really a promising technique to do this. And here I've been involved in a lot of work that has been done with the MUSE spectrograph at the VLT. Now, what makes MUSE so powerful is that we essentially can observe the complete center of a globular cluster. Like this is a 2x2 arc-minute MUSE mosaic of the center of the globular cluster NGC 3201. And then for all the stars that we observe in this image, we can get their spectra, which usually gives us, in the center of a globular cluster, gives us several thousands of spectra simultaneously. Now, MUSE doesn't have the highest spectral resolution. It's only of the order of a few thousand. But you can still do a lot of stuff with it. You could, for example, also measure stellar parameters or abundances. But I'd rather like to concentrate on the radial velocity measurements that we can do with them, and also say a bit about stellar rotation, which we can also measure with MUSE in some cases. So here you see a typical MUSE spectra for one star in this cluster. And now if you observe it over time, if you observe the same image again and again, then you can also start creating radial velocity curves for all of those stars that you see here. And we thought this will be a really powerful technique to study star clusters. So as part of the guaranteed time observations, we started MUSE observations of a sample of currently 26 galactic globular clusters and of the order of 8 massive younger clusters in the Magellanic Clouds. So contrary to the Milky Way, the Magellanic Clouds also host massive clusters in excess of 10 to the 5 solar masses that have formed rather recently. And in our strategy, we from the beginning, we included a monitoring for of the targets to find binary stars. And so far, the observations have resulted in about 2.5 million spectra of the order of 600,000 stars. But maybe pictures say more than words. So this is kind of a mosaic of all the observations that we took of galactic globular clusters so far. One issue that we faced when we got this data was that in the very centers of these clusters, the stellar densities were often extremely high, and they were so high that even with an integral field spectrograph, you couldn't resolve the individual stars anymore. So this is shown here for the globular cluster M80. Fortunately, MUSE has recently been equipped with an adaptive optics facility. And this actually works extremely well, given that it's operating in the optical. So what I'm showing here is a plot from a paper that Fabian Göttgens, one of our PhD students in Göttingen, is working on, where he analyzed MUSE adaptive optics data of this star cluster. And this is the adaptive optics image that we can get of this star cluster. And remember that for each of the stars you see here, we can get a complete spectrum. The nice thing is that the spatial resolution in this image is about a factor of 2 higher than in the corresponding HST image. So I think this quite nicely demonstrates how powerful adaptive optics will become in the in the near future, especially looking to the ELT. But let me come back to what we can do with this data scientifically in terms of binary studies. So the first cluster for which we had collected enough epoch to do a detailed study of binaries was NGC 3201. Here you can see all of the observations set, all of the pointings we took in this cluster. And here you can see like the time coverage between our different observations of this cluster. In total, we obtained of the order of 15 epochs for each of the fields that you can see on the left-hand side. Here is a color magnitude diagram of all the stars in our sample. And just to give you an idea of what we're then dealing with if we want to search for binaries in these objects. So like here are all the velocity measurements for a star that doesn't show any variability in our data. That's the green main sequence star that you can see here. On the other hand, for this red giant star, highlighted in blue here, we see some clear variability in its radial velocities. And now during his PhD thesis, Benjamin Giesers, who was also doing his PhD thesis at Göttingen University, he developed a method to use these measurements and then come up with statistics that predict how many binaries are in our sample. And for NGC 3201, he found that of the order of 17% of the stars show variability in their radial velocities. Now, of course, if you do observations, they are never complete. So we compared them to Monte Carlo simulations that have been tailored to this cluster, which come from the MOCA database. And they allowed us to correct our measurements for completeness and for radial trends. And in the end, we came up with an overall binary fraction in in NGC 3201 of the order of 7%, which is in good agreement with previous photometric estimates for this cluster. But since we have spectroscopy, we can actually go one step further and try and characterize the individual binaries. However, there we're facing a significant challenge in the sense that we typically have only a few data points, but an unlimited number of possible orbits that a binary can have in such a globular cluster. Fortunately, someone else already thought of this problem, and there's this software package which is called the Joker, which essentially creates a massive library of the order of 1 billion possible orbits, and then compares the data in a very fancy way to all of the orbits in this library, and then comes up, then gives you a prediction of the orbits that agree with your measurements. And you can see the result of this Joker analysis here for one star, where essentially you see that the orbits returned by the Joker can be categorized into two families. One family of highly eccentric orbits with a shorter period, and one more populous family of rounder orbits with a longer period. Now, in his PhD thesis, Benjamin did this analysis for all the stars in our sample of 3201. And he was actually able to find of the order of 80 unimodal solutions and an additional 17 bimodal solutions. So a bimodal solution would be this, where you have two families of possible orbits, and then if you only have one family, then this would be the ideal case where you have a unimodal solution. And all the stars that we could analyze in this way are shown here in the period eccentricity diagram. Since we can use the isochrones, since we have a good idea of the stellar masses of the stars that we observe in globular clusters, we can also get minimum masses for the companions of those stars. And this is shown here. We have the fitted minimum masses of the companions and in blue, and then when we try and make a statistical correction for the inclinations, which are always uncertain in our measurements, then we get the mass spectrum shown here in orange. But there's actually a few stars missing in this mass diagram because they didn't fit the scale. In total, we found 4 stars for which the minimum masses of the companions were above 1 solar mass, which is about the maximum mass for a luminous star that you can expect in a cluster as old as 3201. And I've shown here 3 of the 4 examples. The other one was the one with the bimodal solution I showed 2 slides ago. And you see that 2 of them have a mass in excess of the maximum mass that you expect for a neutron star. And we present them as stellar mass black hole candidates in this cluster. So we're pretty confident that our analysis there revealed 3 stellar mass black holes that survived in this cluster 3201 for about a Hubble time. And then the one shown here to the bottom left would be a neutron star candidate. They have, following the first detection of a black hole that we reported for this cluster, there have been also modeling approaches that kind of created models tailored to this cluster. The first one was by Kramer et al. 2018, where you can see here the masses of luminous companions orbiting around black holes in their simulations. And here you can see the eccentricity and the semi-major axis of the orbits. The blue cross is the first black hole that we detected in this cluster, which seems to be nicely covered by what's found in the simulations. The 2 black holes we discovered briefly afterwards, they seem to agree in terms of the semi-major axis, but they seem to also have a lower eccentricity that's predicted than what's predicted by the simulations, which I find quite interesting. However, afterwards there have been new studies of these clusters with simulations, and kind of the number of black holes has been a bit revised, and it's now believed that the cluster can host up to 80, maybe 80 black holes in its core. We're also we're expanding this study to more clusters from the sample, because we want to investigate how the number of black holes we can detect scale with cluster properties. Because if you look at a globular cluster, you can actually kind of see whether it might harbor black holes. Because black holes, because they're so massive, prevent the bright stars from accumulating in the center, which then results in quite a puffed up core if you observe this cluster on the sky. This is shown here, where the surface brightness profiles of different clusters are plotted. 3201 is shown here in orange, and the 2 clusters we're looking at right now are 47 TAC, which is shown here in green, which has a much denser core, so it's believed to host less black holes than 3201. So this is a prediction from models by Eno Brunet et al., where they predict that something like maybe, on average, you would get something like 400 solar masses or so in black holes in this cluster. On the other hand, another cluster we're looking at is Omega Cen at the moment, which has a very extended core, so it might contain actually a lot of black holes. Here I'm just showing the first results that we obtained for 47 TAC. This is work done by a student in Göttingen, Robert Willer, who looked at the data. And yeah, here again you see the stars with good solutions that we have so far. And so far we didn't detect any obvious black hole candidates in there. However, we do have some candidates for massive white dwarfs or neutron star companions. And also what's interesting is 47 TAC is studied extensively in X-rays, and a lot of our detections are actually seem to be optical counterparts of X-rays. But I want to invest the remainder of this talk and ask the question, what about black holes in younger clusters? like those young massive clusters we find in the Large Magellanic Cloud. And I'm showing you here two clusters that we recently have observed in more detail. NGC 1850, which is only 100 million years old, and NGC 1846, which is about 1.5 giga-years old. Interestingly, though, these data were originally taken for a completely different purpose, which I think also shows you how versatile integral field spectroscopy is. Because previously people looked at their color magnitude diagrams and they found some strange things. Like if you look at NGC 1850, then you see that the main sequence actually seems to split up in two separate main sequences here. And also, if you look at NGC 1846, you see that the main sequence turnoff that you see here seems to have a very large spread in colors, which might actually even be bimodal. And then the question was, what causes these splits in the color magnitude diagrams? The first idea that people came up with was that it might be age spreads, because you see here for the example of NGC 1846, that you can actually nicely explain this spread if you assume that there's two different populations living in this cluster, separated by of the order of 300 million years in age. But there were some things wrong with this scenario. For example, the age spread was the higher, the older the cluster was, which doesn't seem to make sense. So yeah, people looked for different explanations. And one of the explanations was stellar rotation. Stellar rotation essentially changes the hydrostatic equilibrium in a star. So it changes the effective temperature as well. And then this could also lead to the spread, as you can see here when you compare the photometry for 1846 to isochrones for different rotation rates of the stars, relative to the rotation rate where they would start kind of disintegrating. Now, in order to check whether it's really stellar rotation, you need good statistics and you need spectroscopy of many stars, which unfortunately are quite faint. But here MUSE can really make a difference because MUSE is quite efficient, so we can actually observe these stars which are fainter than 20th magnitude. And when we did this for NGC 1846, we really found that different stars seem to have different rotation rates. So here you can see that the star highlighted in red has much broader calcium triplet lines than the star highlighted in blue. And if you compare these two template spectra, you find that the blue star is rotating rather slowly. We find an upper limit of something like 45 kilometers per second, whereas the red star seems to be rotating at about 160 kilometers per second. Now, when we did the full statistics and plotted this over the color magnitude of diagram of this cluster, we could reveal this clear trend between the inferred rotation velocity of the stars and the position in the CMD. And if we just take a look at a short range in magnitude, then we see that there's like a clear correlation between the measured V sin I and the color. And you also see that if you make a histogram of V sin I values, then you see kind of two clear distinct peaks popping up. So we really seem to be having one population of fast rotating stars, which makes up about 55% of the cluster members, and another population of slowly rotating stars in this cluster. What's also interesting is if we go to to fainter magnitudes, we see the disappearance of the peak of fast rotating stars, which can be explained by the fact that we're entering a mass regime below, say, 10 to 1.3 to 1.4 solar masses, where stars have convective envelopes and are effectively braked by magnetic fields. And what I'm currently working on is doing the same analysis for NGC 1850, where we seem to find something very similar, where you see here the stars along this blue main sequence, which seems to be consisting mainly of slow rotating stars, whereas the stars in the main sequence are rotating a lot faster. But coming back to one thing, the question then was, what causes these these differences in the stellar spins? One solution here was, again, binary stars. So maybe all stars are born fast rotators, and then if you have tight binaries, you start tidally breaking the stars. However, the MUSE data, which for 1846, which was taken over several nights, revealed similar fractions of binary stars for the two populations. So we concluded that binaries are unlikely to play a dominant role here. And then in a paper that I did together with Sebastian, we proposed that maybe it's the lifetimes of the pre-main sequence disks that causes this. If you want to learn more about this, please ask me after the talk, because I wanted to use the last 1-2 minutes to tell you how we are currently using these the same data to search for black holes in these clusters. And this is work that's led by Sara Saracino, a postdoc at our institute. And she started looking at these data and started looking for stars that show clear radial velocity variations. And on the right-hand side here, you can see as small black points all the stars that in NGC 1850 show radial velocity variations. And the stars highlighted in red are those that have the highest peak-to-peak radial velocity variations. Now, NGC 1850 would be very interesting if one could look for black holes in this cluster, because it's only 100 million years old. So evolutionary effects don't play much of a role, but the black hole population should already be fully in place at this age. So Sarah then again looked at the Joker and started analyzing those stars. Unfortunately, back then, if you only have something like 5 or 6 radial velocity measurements, then it's unlikely that you can already constrain the orbit completely. But you can already kind of get an idea of what family of orbits matches your data. And this gives you then a median companion mass that you can need to explain your data. And we found that some of those stars with very high peak-to-peak velocity differences also have companion masses which would be above the main sequence turn-off mass in this cluster. And for NGC 1846, we found something quite similar. So we went back to the telescope and asked for more time, and fortunately we got this, and we recently got an additional 10 epochs for both of these clusters. And with this new data, we're actually now starting to be able to really constrain the orbits for both of this, for the stars in both of these clusters. So here you can see, for example, from Sarah's ongoing analysis, see one radial velocity curve, which nicely seems to suggest an orbit with something like a bit more than 400 days, and where the companion mass might already go into the regime where we cannot explain it with a luminous star anymore. But this is really preliminary work and ongoing right now. Now, I think I'm mainly really out of time with the 40 minutes that was anticipated. I had 2 slides on intermediate mass black holes, but maybe I will skip them in the interest of time and just leave you with my take-home messages. But if you want to know anything about intermediate mass black holes, then just ask me.
Thank you very much, Sebastian. It was a very nice talk. Do we have any questions? If you do, please write your name in the chat. In the meantime, I have a question. Will they start popping? I'm curious about the black hole candidates that you mentioned in one of the globular clusters, or it was probably several globular clusters. It was 3 candidates. Yeah. And I'm wondering whether you could tell us a little bit about the properties of the stars themselves, the luminous objects, what kind of masses they have, what kind of spectral types.
Yeah, so that's a good point. So let me start with the first one we detected. We were really lucky because this is This was like subgiant branch star, so it was located somewhere here. Yeah, it was like a 0.8 solar mass subgiant star. Was the temperature of I don't know the stellar parameters out of my head. I would need to look them up.
And the periods, you remember the typical periods maybe that you?
Yeah, so that's that's this one. So it's 167-day period.
Okay, so very far from Roche-Lobo refueling or anything like that.
Yes, yeah. So and the other two are really main sequence stars. So and with this first black hole, we got kind of lucky because it was in the overlap region between two pointings. So that's why we got like twice the amount of measurements for it than for the other stars. And when we reported on the discovery of this black hole, we hadn't analyzed all of the data yet. So it was really reassuring to see that the data that was taken after the publication actually fitted the orbit that we had determined previously.
Mm-hmm. Okay, cool. Thank you. Julia has a question.
Yes. Thanks a lot. Very nice talk. Actually, I'm also curious about these three candidates, or also their comparison to the prediction from theory. So you said that at some point there was predicted to be 200 black holes in that cluster, then later was a bit reduced, but still it doesn't really match, right? Because if I see it correctly, then around 40 black holes were predicted, and there were 3, if I got it right, that were found. So where's the rest?
Yeah, so that's a very good point. It's kind of, it's a bit of a problem that we're usually only seeing the tip of the iceberg, because it's predicted from stellar evolution that most of the black holes should be in binaries with other black holes, because what you happen if you have a system like our system between a black hole and a subgiant star, if this encounters another black hole in the cluster center in a 3-body encounter, then it's very likely that the incoming black hole will kick out the subgiant star and form a binary black hole with the other one. So that's also part of the reason why globular clusters have been suggested as being very efficient in this, in forming binary black holes dynamically.
All right, thanks.
Yeah, so the number of black holes in orbits around luminous stars that we find, so like 3, seems to agree with what they get from the N-body or Monte Carlo simulations. They typically also only find a handful of stars, of black holes that one could detect because of luminous companions.
And I guess you can fully rule out the presence of a luminous companion given the masses. You would see them, right? They would be brighter.
Yeah, exactly. So yeah, that I know that at least some people from here are also involved in this debate on whether LB1 is a black hole or not. I think we have a big advantage in the sense that we have a pretty good idea of what kind of stars we're dealing with. So if it's on the subgiant branch, then it should be a subgiant branch star.
Okay. Any other questions to Sebastian? Nope. Okay, cool. So thank you very much, Sebastian. We will reconvene in about 5 minutes.